So, we're going to talk about artificial intelligence, machine learning, neural networks, and deep neural networks, how we build them, how we train them, and how we use them for 3 hours, minus the break. So, the countdown is not running. I have plenty of things to tell you, so I have to try to run fast. But if you have any questions or comments or whatever, I guess we can make them fit in 3 hours minus the break. So I've added on, as you can see my Twitter account there, I've added a tweet under which you can post comments or questions. I'll try to monitor that. Doesn't seem to be auto-refreshing, but we'll see. And or by direct message, they are open. You can reference the slide because there are many ones because of animations. So there should be the slide number at the bottom right. And I hope that at the end of this talk, you'll understand how the deep neural networks work, and you'll be willing to pursue this long journey because of course, you would have many more things to learn. And I will suggest you books, videos, and massive online courses. Who's here has already followed a MOOC, a massive online course? Well, I'm asking, but I don't see anything. So, okay, so I hope this will be your first for those who haven't raised your hand. Ready? So let's start with a short introduction about artificial intelligence, because actually we've been promised a lot of things for decades, actually. So indeed, artificial intelligence is a research topic that started in the mid-50s from the last century. About at the same time, we started to have computers with lamps. So not even computers with transistors. So we can ask, what is artificial intelligence, where it starts? And you will see among this talk, the definition or the limit of what we consider as artificial intelligence has really changed over years. When something is new, we are astonished by the new accomplishments, but then we get used to that, and we find that what used to be astonishing is now crappy and stupid, not even intelligent. So, in any case, you can guess that in the mid-50s, with lamp computers, we didn't have many things. So it was more research and so on. So there's been a lot of promises made. We were also promised flying cars for 2018 or even before. And of course, results didn't match these promises at all. So you may remember, So from that time, you may remember chess computers. I had one when I was young, so it was far more intelligent than I was on this game. But that's almost all we got. And because of all these disappointments around the 70s, the people who used to invest in research around artificial intelligence a bit gave up, and we entered what we called the winter of AI. So some researchers were still working on that, but everything progressed very slowly, especially if we compare to what happened in the past 10 or 15 years. So in the 80s, we still had things that were called expert systems that helped people to make decisions, but the only thing these systems were doing was actually to run sets of rules, more or less blindly, without understanding anything. And first, these rules had to be expressed by humans, and second, they were very limited to specific domains. So it wasn't scaling at all. And for the record, this approach was called symbolic artificial intelligence, as it involved strongly logical and Cartesian reasonings that we could demonstrate afterwards, if given enough time. And in parallel, some researchers were still working on imitating neurons from our own brain or animal brains that we studied. And actually, the core algorithms that are still in use nowadays in deep learning, and most of the seminal principles involved in deep neural networks come from this era. So conversely, this approach is not symbolic anymore, but connectionist, because it reflects the connections between our neurons. This approach gave far better results in more and more domains over time, but in exchange we can no longer prove, at least in a formal way, what these neural networks are computing, why they are making some choices. This may sound very fuzzy, but that's actually how we work as well. We are not always able to explain why we made some choices. So the connectionist approach is more based upon intuition, we could say, rather than Cartesian reasoning. So at the end of the 80s, one of the first achievements of neural networks that started to be a bit deep was the ability to recognize numbers from zip codes or scribblings on checks. And that's one of the results we'll study later on. So, for instance, this kind of scribbling. And something you may remember have heard from this era was in 1997, when this huge computer from IBM, Deep Blue, won for the first time against the world chess champion Garry Kasparov. So once again, Deep Blue was mostly a machine able to compute the outcomes of possible moves very quickly at a rate of 200 millions moves per second. So that's called brute force, and that's not the way human thinks. But at least that was good enough for chess. And anyway, this brute force approach doesn't scale with games like Go. So we have to find something else. So there's been other progresses, but the real breakthrough of artificial intelligence and neural networks really came during this past decade or so with deep learning. And in 2007, so 10, 11 years ago, some researchers started to build the ImageNet library that now contains more than 15 million of images labeled with their content and the bounding boxes of this content, such as this one. And every year, this set of images was used in competitions among researchers. First with what we could call the generic or standard approaches. And in 2010, so only 8 years ago, with different conventional approaches, the best results were about 75 of accuracy. So that means that one result output by these techniques out of 4 was plain wrong, only 8 years ago. And in 2010, 12, so 6 years ago, convolutional networks that we'll see later on were introduced, and immediately they won the competition by more than 10% accuracy with respect to the second best technique. So since then, researchers have elaborated neural networks architecture and training techniques, even more powerful. And nowadays, on this database, I guess that errors, the level of errors is about 2%. So it's on par with what we call human-level intelligence. And since then, we have moved to more complex image database like COCO and so on. We've moved to image segmentation, meaning that we know not only draw the boundary boxes, but we also paint the components or the objects, sorry for the little girl or whatever, and the dog. So we paint really the different objects on the picture. So, since then, you've all heard that, Neural networks have been applied to many domains, and sometimes with spectacular results. And we are now able to perform image recognition in real time for cars and traffic signs and so on. And this is the basis for autonomous cars, without even requiring a heavy network computer. So nowadays, still machines can beat any human at chess without having to evaluate billions of moves in advance, and we know how to achieve that for the game of Go, but again, without brute force. But we won't be able to see in 3 hours the technique that allows that. In other topics, in terms of voice recognition and natural language processing, it looks like we are almost on par with human level intelligence. The translation between the most common languages seems to be well advanced. Speech synthesis is now really bluffing. You can't really tell if it's a computer talking or human. So we should soon have real-time translation. Okay. So eventually, one of the really breakthrough that fascinates me the most is autonomous cars, because driving a car almost become an unconscious process at some time. You completely forget what you are doing. But it's actually very hard to drive a car if you think about it, if you concentrate, without killing anyone, I mean. And right now, there are currently, I mean, if they woke up at that time, there are autonomous cars that drive all by themselves, mostly in the United States, I think. So indeed, it's currently limited to authorized areas, in places where the sun always shines, where there's never rain and so on. But we are progressing, we are getting there. And several companies are really doing that, not only Tesla or General Motors or whatever, and Uber. So things started very well. Well, it was promising for artificial intelligence and neural networks. And then almost everything froze to death during the winter of AI. So, do you know what caused the global warming that respawned research around the AI? Anyway, I can hear you. So, two things changed the picture, actually. First, video games. Or actually, the graphical cards with their GPUs that power these video games. And at their core, GPUs can do many things. They are not generic like CPUs. They're only good mostly at performing additions and multiplications. That's it. But they do that very fast and in parallel over thousands of core. While CPUs only have 8 cores in laptops and workstations, maybe 40, 50 in servers, and they have vectorized instructions to process maybe 256 or maybe 512 instructions at the same time, but actually they can't compete with the GPUs, really. And the additions and multiplications, or in the reverse order, that these GPUs perform very fast are really at the core of what we do when we train or run neural networks. So we really needed GPUs for that. And actually, this was the first graphical card or GPU to be programmable, because formerly it was only used by specific APIs dedicated to compute polyfills and whatever, and shading and for games. So then things improved. We went from graphical processing units to new, whatever that's called neural tensor processing units, which are really dedicated to neural networks. So without any graphical output, you can plug a monitor on them. And NVIDIA is still the leader in that field. So they have introduced libraries ready for developers to use their GPUs for neural networks. Google introduced their own chip, tensor processing units. And now we have, in data centers, we have blades really dedicated to running GPUs with tons of memory, because we also need a very fast access memory. And all networked so that we can parallelize computations over multiple GPUs and multiple machines and so on. That's industrialized. And you can rent these servers on Google Cloud or Amazon, etc. So this is important, having all that computational power, because working on neural networks is a very iterative process. First, you need to have an idea. Then you have to experiment with this idea. That means to implement something, implement a neural network. We'll see that it's not the most complex part later on, but still you have to do that. Then you have to train it, and it takes a lot of time. Then you have your results. You have to figure out what's wrong, what could be improved, and so on. And then you iterate again. So really using GPUs can give you a boost of about 2 orders of magnitude over CPUs. So that means turning weeks of computations to hours, etc. So it just made things that were untractable because of our patience or lack thereof really doable easily, let's say. So if you're ever getting serious to do neural networks, you need a GPU either in your machine or in the cloud. So the second thing that allowed neural networks to flourish was the era of big data. So in order to be trained, we'll see that we can save a bit on that topic, but a neural network needs tons and tons of examples. So if you're working on cats and dogs labeling, you need thousands or tens of thousands of images. Ditto if you work on traffic signs or car recognition, there are many shapes and so on. If you work on videos, you need hours and hours of video. If you work on natural language processing, you need hours of speech, written, pronouns, etc. So the tremendous improvements we've seen in, again, the last decade or so on network bandwidth and storage space and the advent of data centers have enabled this big data area and thus gave us enough data to perform neural networks training. So let's dive deeper. What is actually machine learning? So how do we teach children, humans? For instance, when we have a kid and we teach them to recognize dogs and cats, how do we do? Do we give them a set of physical descriptions, like the number of legs, the kind of fur they have, the form of their ears, of their eyes, are they mammals or not, what sound they make, etc.? No, we don't. Of course, except if we want to train them to become a vet, we just say, this is a dog, this is a cat. We may repeat that a dozen times. Okay, we are patient as parents. And at some point, the kiddo should figure out how to distinguish cats and dogs. And machine learning is about the same. If we apply that to computers, in what we may one of these days call old-fashioned programming, we have programs that really implement explicit instructions, implicit decisions, and dedicated algorithm. You have to rewrite your rules, your if-then-else, for each and every topic you want to support. So, in a nutshell, we implement decision trees. But what happens when the volume of these rules become too complex to express by a human or in the code? Yeah, sorry. If you raise your hand, I really don't see, so do that clearly. So think a bit if you had to implement an autonomous car system. Where's my picture? Actually, an autonomous car system is a system with very little outputs. You have to steer the wheel, brakes, accelerator. Sometimes you can blink to warn that you are turning left or right. We don't do that much where I live. That's mostly it. So one angle, speed control, that's it. Seems very simple. Do you realize what it should take in classical programming to implement all that? First, to discover the road, the limits, read the signs if we have any, figure out the slope that you have to reduce your speed before to turn and then speed up afterwards. It's extremely complex. And then, how do you handle that? I don't know. So, machine learning, when we do that, we forget everything that is related to explicit programming. And we instead set up rather generic systems and algorithms that will enable the computers to learn almost by themselves, using tons of examples, with the guidance of a feedback method that will tell the system how to correct its output, its predictions, and toward which direction they should go to improve their results. So, also data science. Sometimes it's a fuzzy word, we don't know what's behind that. So, the goal of a data scientist is, from past data, to build a model that will allow to perform predictions on future data. So, for instance, by studying past sales on some product, we can try to predict what will be the future sales, depending on the weather, on the temperature, on bank holidays, and so on. For a bank or an insurer, we can try to detect fraudsters who have deviant behaviors with respect to what could be considered as a regular behavior, and so on. So, being a good data scientist is quite complex because we expect these people to have a lot of diverse and complex competencies. So, for instance, a data scientist must be very good at math, especially statistics. He must be able to work with large data sets that are often not visualizable on screen or whatever. He must be, or she, able to understand the employer-specific domain. He or she must have a hacker mind, because sometimes we have to tweak the data in some form to reveal things. And he or she must be able to program as well, usually in R, which is a very statistics-oriented language, or Python, which has been adopted a lot by, let's say, non-developers as well. So, deep learning is supposed to make that simpler, but stated this way, this sounds like data scientists are superhumans, but there may be some discrepancies with the reality. So actually it seems that in real life, data scientists spend a lot of time to curate data in order to make them really usable. Because when we build a model, be it a classical one or deep in your network, if you push in trash, you will get trash out. So data have to be normalized, empty or missing values must be set to something, errors must be corrected, and so on. And okay, I thought I had another slide. Good. So let's skip the introduction. I would like to insist on, no, that's later on. So before we start talking about deep learning precisely, we have to understand that deep learning is only one side of the multi-sided coin, and there are many techniques in machine learning to analyze data and build models of them. So first, we can distinguish three main types of machine learning approaches. In the first one, called supervised machine learning, we build our models with data for which we know the correct answer. We have labeled data. The goal of the model will be to find the relationship between these data, which are split in features, we could consider that as properties, and the result we want to predict. One of the goals could be to perform regression. So this term is not very intuitive. It comes from historical reasons. But the idea behind regression is to predict a numerical value, like the temperature, the value of some share, the number of individuals in some population, whatever, from different data features that seem relevant. A second goal of supervised learning would be to perform classification, like, for instance, to describe the content of a picture, as we've seen with the bounding boxes, or perform medical diagnostics. So in any case, in supervised learning, we have training data that have labeled with the correct answer, hopefully. The second main type of machine learning is, conversely, unsupervised learning, in which we have data on which we want the machine, all by itself, to find structures, relationships that we are not aware of. So this may sound puzzling at first, but for instance, we may want to find groups, clusters of, so subgroups of data within our global set, subsets of data that could be considered as similar. So for instance, in order to segment a customer database, to recommend, to perform recommendation or display different ads depending on the target, and so on. And we could also try in big data set with tons of features to reduce the dimension of these sets, reduce number of features, in order to make them visualizable. And the third set, which may in a few years become the most predominant type of machine learning, it's the reinforcement learning. That's what we use to, it's even less unsupervised than unsupervised learning. That's, for instance, the techniques that have been used for the game of Go, or if you've seen this system from Google, I think, which learned by itself to play some Atari games. They were only telling it, okay, you have to maximize the score at the bottom right of the corner on the screen, top right, or whatever. And the system did whatever, random movements. Then it was noted, evaluated with respect to this score on the screen, and it tried to adjust its movements in order to beat the score. So this takes a very long time to train, but in the end, this kind of resulting program can beat anyone at Pong or whatever games, I don't know really. So we won't be able to see that in details today. So for each of these problems, and the list is far from being exhaustive, these were just a few examples, there exists a solution that relies on neural networks. But don't think that neural networks are the only possible solution. That's the law of the instrument. When you have something good, when you have a hammer, everything looks like a nail. So one of the difficulties of a good data scientist is to figure out at each time which technique is the most appropriate one to use. Okay, does anyone know Python at least a bit? But I guess you won't be lost if you don't know Python. What we are interested in the field of neural networks or machine learning in general, it's a reduced ceremony language. You don't have to create objects like in Java or whatever. It's multi-paradigm. Okay, you can do anything you want anyway in this language. It's interpreted, so it may be shocking to hear that we are using an interpreted language to run heavy computations like the one we need, and to drive them on GPUs and so on. But actually, most of the hardcore libraries that perform mathematical computation are implemented in C, and you can call them directly in Python. So you don't really care about the loss in terms of speed. You have automatic memory management, so it's very nice. And it has built-in support for list, tuples, and multi-dimensional arrays, and slices as well. It's often very useful to be able, in one expression, to slice an array or quickly. And there are tons of packages and libraries. It's really a big mess, but anyway. So, another definition. What are tensors? So that's a word, I guess, which is probably frightening at first, because most of us, I guess, have only heard about tensors from Einstein and its relativity theory. But actually, we can imagine it's simple. I'm supposed to have a slide there. Did I hide it or what? Sorry for that. Okay, it was hidden, indeed. So, tensors. Where is my view? Good. So, let's start with the basics. Remember your math from the school. A scalar is a single number, like 42. It has no dimension. You don't need any index to access its components. It doesn't have any components. A vector is a one-dimension set or list of numbers. Here we will be only using floats for the record, not really integers. A matrix is a two-dimension array of values. You need two indices to access all the components. And a tensor is the generalization of all that. So it's a bit hard to represent a tensor maybe beyond 3 dimensions. Some people have tried to represent that on screen. But anyway, I think as developers, it's a bit easier for us to represent what a tensor may be, because a scalar is just a float, a vector is an array, a one-dimensional array of floats, a matrix is a two-dimensional array of floats, and a tensor is the generalization of that. So it's something a bit complex when you practice it, because when you perform computations, for instance, matrix products, you have to have the right, on the left operand, the number of columns must match the number of rows. And when you manipulate tensors, it's a bit complex to figure out, but there are helpers in the code. So a tensor is just a generalization of a matrix. Okay? So let's start with a first problem that is called linear regression. Once again, the term is not really self-explanatory. It comes from a statistics history. So the point of linear regression is to find a relationship between a set of data, a set of features, and one result. So let's imagine that you have inherited a small house, but there's always some kind of noise, dripping water or whatever, and you don't want to keep it, you want to sell it. And you don't want to hire a realtor, you want to sell it by yourself on Craigslist or whatever. So you have to figure out the price of this house. How do you do? We're supposed to live in a world of open data. So, okay, you just grab all the recent transactions that have happened in the neighborhood, and you try to extrapolate the price of your new house from the similarities or the differences from the already sold houses. So, more formally, we want to predict the sale price of this house depending on characteristics like the living area, the number of bedrooms, the number of bathrooms, the area around the house itself, the neighborhood, and so on. That's where data curation happens, because all these values have different scales, and they have to become comparable. You don't want to mix apple and oranges in there. So you have to convert a price in the end, which may be a very large value, from a very small number of bedrooms and a large living area surface. So that's where curation happens. So what we want is to find a mathematical function, hopefully linear, that will give us an approximation of the stash of money we could get from that. Let's simplify the problem and only keep the living area as an input of our problem. Okay, so in Python, we'll first load our transactions that we've gotten from whatever. This is just a few lines of Python, the method, and there are libraries like pandas for that. Pandas is a kind of Excel for Python. It's very powerful. And in one line, we can load the set of surfaces and the set of prices from our data set on the left. So we can print that it's an array of values and so on. So we can plot this data as a scattered plot. And yeah, we can see that there's almost a linear approximation of this curve. So of course I have generated these values, so that's why they fit, but it's more simple. Let's keep a first order solution and not larger orders polynomial solutions. So we have simplified the feature, we only keep the surface, we have the price as a result, and our goal is to find a system, a program, an algorithm that will allow us to find this red line iteratively. There are, of course, mathematical solutions to that. I guess it's the squared, I don't know the name. But anyway, this technique doesn't scale to a large number of features, of properties, and it won't be applicable to neural networks. So we want something really, a generic algorithm that could find any kind of solution to problems of this kind. So, if you remember from school, the formula for this line is ax plus b. Everyone is fine. I guess we can move on. And so in Python, we have the NumPy library that contains tons of mathematical functions. And to be honest, there's already a polyfit method that will get your two sets of data and will try to return the best approximation on a linear function here, because I asked for a 1 degree solution. And it will return this, that we can convert in a lambda, in a function, which prints this kind of parameters. Okay, so it already exists, but once again, this doesn't scale. So we want to implement our own. So, let's imagine that we start with this result, which is obviously wrong. We are far from the correct solution. How can we correct our error and refine our proposal? In order to do that, we have to figure out how far we are from the solution. So that's it. We have to compute the distance between our current solution, the red line, and the correct one, which is a bit upper. So in order to compute the distance, that's easy. We just have to take all the points one by one. We have the result. Y is the correct value. Y hat, by convention, is our prediction, which is wrong for the time being. We have the equations. They are linear. That's OK. And we can compute the difference between the two. That's easy. And we can perform that for all other examples. We can sum up all these small distances. But if we do that, and we can average them, so I divide by 2 because this simplifies some other formulas in the future, but it's a detail. So we just divide by the number of examples we have, and then we have the sum of distances. So the problem with this method is that if we have some results that are, or some predictions that are above the correct line and some others that are below the correct line, they may cancel out each other with the subtraction, or the sum actually. So a good idea is to compute the square of this distance so that we only have positive values. And actually the square will amplify the errors. So it's even better. Okay? So we have what we call a cost or loss function. It's express the cost of something that we want to reduce, or loss that, once again, we want to reduce. That's a linear, or no, it's a squared. So it's a squared equation, so we can plot it. Yeah, I've inlined the value in there. I guess you still follow. Okay. So this is a second order polynomial, so we can still print it on screen or graph it. That's fine. We can see our two parameters, that A and B, that's what we want to find as a good approximation of the semi-line we had as input. And as you can expect it, we have a kind of parabolic curve surface as we have a second order polynomial. Good. So we can notice with the red spots that if A, the slope of our linear regression is too small or too large, the cost function at these points will be far from the optimal, which is the green spot really at the center of the bottom. We don't see that very clearly of the parabolic surface. Ditto for B, if it's too large or too small, we are far from the optimal value. So the question is, how can we find the location of the green spot that minimizes our cost function and will give us almost a perfect fit to our data? Let's forget about that. So let's imagine that our algorithm starts randomly, or almost, not really, from initial values 0, 0, which is this red spot there. How do we do, mathematically speaking, to figure out that we have to get down the slope towards the green spot incrementally? Hey, it's not nap time.
Take random values.
Yeah?
You take random values and you see if it's better?
Okay, you take random values. I guess it's the annealing, simulated annealing algorithm. No. How do you know where a slope is going with math? Yeah, the French one. So derivatives. Yeah. Do you remember that? It's high school. So that's the core algorithm at stake in neural networks, deep neural networks, and so on. It's called gradient descent. So in mathematics, the concept of gradient is the generalization of the concept of derivatives for functions of more than one variables, which is our case here, as we have two parameters, A and B, that we need to find. And this will be even more the case when we will use larger neural networks, as we will have thousands or millions of parameters. So, computing the gradient or the derivatives of a function with the several variables may seem a bit complex. I remember that I understood how it worked at the end of the exam at the university, so it was a bit too late. I focused a bit too much on computer science. And actually, it's quite simple. The point is that we compute the derivatives for each variable, which means that all other variables are considered as constants. And if you remember, it's very easily to derive constants. So, do we have more explanation? Let's compute the derivative of j. It's okay if you skip that. So if you remember, it's called delta j over delta A. So that means how does J increase by a delta when we increase or decrease A by delta. And if you remember, that's a very mechanical process, actually, to compute the derivation of a function, even this one that seems a bit complex. So I guess we'll skip that. But if you trust me, that should be it. OK? I guess you don't need more details. OK, we can do that as well for B. And we have a more simple equation, because we don't have a composition of function, I think. Or yes, we do. But anyway, let's keep that this way. In any way, really computing derivatives is a very mechanical process. So that means that it has been automated by computers for decades, I think. And we have libraries that perform symbolic computations and symbolic derivations for decades. But we are here to understand what happens under the hood, aren't we? OK. So let's get back to our gradient descent toward the bottom of the shape algorithm. We have our cost function j that we want to minimize. So we are looking at the coordinates of the green spot. And we start arbitrarily from the origin, 0, 0, on the red spot. So what we are going to do is very simple. For each iteration, we are going to move towards the pit by little deltas using the partial derivatives. Because a derivative gives us not only the direction of the slope, if it's upwards or downwards, and also the steepness of the slope itself. And in order to figure out how much we are going to advance at each step, we need what is called the learning rate, which we will call alpha. So we are just going to multiply at each step the derivatives at the current point for a given axis by this alpha learning rate. So the alpha learning rate is a bit hard to choose, because if you choose it too small, you will make too small progresses at each iteration, and you will need hours and hours of computation to converge. And conversely, if you choose it too large, you will jump on the other side of the mountain, let's say, and your algorithm will never converge. So that's why work on neural networks is very iterative. So anyway, by the way, this alpha is called a hyperparameter in the properties of your system. The parameters are the values that you want to find with this kind of algorithm. And the hyperparameters are all the settings that are around your system that you have to choose by yourself. And there are also automated approaches for that, but still. So let's see that in action and let the ball loose with our algorithm. So we can see that at the beginning, the ball was running quite fast, because the gradients, at least on the a-axis, was quite high. And then at the end, the derivatives are smaller. We are almost on a flat region. So the progress are smaller. So let's notice already that if the ball, maybe I can rerun that. If the ball was really a physical one, it should reach the green place faster, because it would have acquired momentum when it went downwards. In this case, with this algorithm, we don't have any memory of what has happened in previous steps. So we don't have any concept of velocity. We are always going at the same learning rate. So we'll see refined algorithms that take this idea of momentum in action later on. So let's forget now about these partial derivatives. I guess you have understood the overall idea. And let's rise up. So, our algorithm was actually divided in two phases that I propose to represent this way. We have a first pass of forward propagation, where we propagate in our graph of computations our learning data. In here, it's the x value. We multiply it by a first parameter a, then we add a second parameter b, and we'll keep an empty cell for later on. And this gives us a prediction y hat. Okay, good. Then we have to compare this prediction using a distance with the ground truth, y, that we know is correct. And from there, we can compute a delta that we combine with the learning rate. And then we perform a pass of backward propagation in which we correct the values, we adjust a bit the values of our parameters a and b by a little delta, hopefully towards the correct direction. And then we repeat this process as many times as needed for the ball, the red point, to reach what seems to be the most efficient, the optimal solution. Okay? So, one important thing to keep in mind is that we have really simplified our problem. So, in this 3D representation, we can check that of course, we wouldn't know where the green point is, although we can visualize that. But on this representation, we can see the red ball rolling down. So we can figure out when it should stop. But in real life, don't forget that we have many more features in our problem. So we won't be able to represent that on screen and see how it progresses, when we can stop computing, and so on. So we have to monitor the progress of our algorithm with something else. In this case, we have a function a and b with two parameters. We would have many more in real life, but it's still a function that gives a single result. Okay? So we can forget about that and plot this function, actually. The goal is for it to reach 0, ideally. Of course, we can go there if we don't have an exact fit of our data, and we'll never have one. But we want it to be as close as 0 as possible. And we want to see where or when it reaches an asymptote, which means that we can stop our computation, we are not progressing anymore, and we have found the optimal solution. So let's try to do that in parallel. That's the plot of our cost function. Okay, we are repeating all our forward and backward propagations, and it looks like we have reached an asymptote. So we could stop the computation right now. Okay? So let's synthesize what we have found so far. The general recipe for solving this kind of problem, and it will actually be the same with deep neural networks, with image recognition, natural language processing, and so on. At least in the world of supervised training, it's to have labeled examples. We need a training set on which to train our models, and we need a lot of examples. We need to define a cost function, which clearly defines the distance between our predictions and the ground truth. Then we have to compute the partial derivatives of this cost function, which will provide us with gradients for updating our parameters at each step of the process. Then we have to perform as many loops as necessary of forward and backward propagations. We compute predictions for our parameters. We compute the cost or the distance with the ground truth. We compute deltas, and we propagate back these deltas by correcting parameters. And we can monitor this cost function to figure out when it reaches an asymptote, which means that an optimal solution was found, and there's no more need to compute anything. Okay? Was that simple enough? Let's do something a bit harder, trying to decipher scribblings, human scribblings. So this problem is a bit the hello world of neural networks and image recognition. It's called the MNIST database, and it contains 70,000 labeled digits of this kind. Some are easy to read, some less. And it's so much the hello world problem of neural networks that it's included as an additional package in TensorFlow. So it's very easy to get your hands on this database and play with it. So this database was assembled by Yann LeCun and his colleagues, and this guy was a pioneer in neural networks, especially in convolutional neural networks that we will see later on. And he's now the big chief of the artificial intelligence lab in Facebook. And on his site, I've added QR codes of URLs in a few slides, more in the end for books and MOOCs and so on. So you can take a picture if you're interested. On this site, there's a list of all the methods that have been tried over the past decades, 3 decades, to recognize these digits. And we have sorting of results with their accuracy. So it's quite interesting. So for instance, this, in this database, each image is stored as a matrix of 28 by 28 pixels with 256 levels of gray. So it's black and white or gray. So matrices are a bit complex to handle. So we'll simplify our problem by converting this matrix into a flat vector of 28 by 28, which is 784 pixels. We'll also normalize the values so that they are between 0 and 1. It's always a good thing to normalize things again in neural networks. So I only displayed 4 pixels because it doesn't fit on this small screen, but we have 784. So this looks a bit like our previous problem, where we had a vector of data. Actually, in real life, we had a matrix in the case of houses, but we simplified that as a vector. We only kept the living area. And we found a way to solve a linear regression problem that could predict the price of a house. Except that in this case, we are not looking for a result in a continuous range of value, like the price, but we are looking at something that outputs discrete value within the range 0, 9 for each digit. And precisely, we would like to have probabilities according to the system for each digit. Does it look, actually, probable that this digit is a 0 or 1 or so on. But could we try to adapt our previous system to this kind of problem? Let's try that. We do the same as before. We perform a weighted sum of all the inputs that we have, this time 784. And we want to figure out the weights, A1, A2, A3, and A784. That would tell that this set of pixels looks like a 0 or not. So I won't draw the weights everywhere because it will be too messy. So keep in mind that for every line that we have in this graph, we have a weight associated. Okay? So we then have to do that for each and every digit. So for 1, for 2, for 9, etc. Which means that in total, in this system, we have 7,840 weights, parameters, that we have to find. Sounds a lot, but it's nothing compared to real-life neural networks. So, at this point, we could keep only the digit that has received the maximal value, which is the most probable according to the system. But we'd like to keep the values as probabilities, because it's interesting to figure out what the system thinks of our pixels. So, more precisely, for each digit, we want to have an associated probability, and we want all these probabilities to sum up to 1, because these are mutually exclusive. So there's a mathematical function for that, which is called softmax. As the name tells, it's not a strong max that only outputs one value, but it keeps all the values, and it tries to reflect the gaps between the values, actually by extending them. That's why we are using an exponentiation, but the formula is not really important. And we divide by the sum of all the exponentiations in order to have a result between, in order to have the sum of results equal to 1. So let's just keep in mind that softmax will take an input of, in this case, 10 values, which are in any range. The largest one will become close to 1, and the smallest one will become close to 0. Okay? So then we have to compare these predictions to our ground truth. And for that, we have just to convert the vector of values to what we call a one-hot encoding of the result. One-hot means that only one value will be equal to 1, and all the other ones will be equal to 0. And then we have to compute a cost function for that. So we could use the Euclidean distance with the square. It's called the Euclidean distance because there are many distances actually in mathematics. So we could use the Euclidean distance, but for problems of classification, it's better to call what is called the cross entropy, which is this function. It sounds complex, but we can see that as an if then else, actually. Y high is the correct answer. So if it's 1, meaning that the digit I is the correct one, log, we want the logarithm of our prediction to be as high as possible, so that the logarithm, so we want the prediction y high to be as high as possible, so that the logarithm is close to 1. And conversely, when the y high is not the correct digit, 1 minus y high will be 1. So we want the expression in the logarithm to be as small as possible, even negative, so that the logarithm is as small as possible. So that means that we want our prediction, y high, to be as small as possible. So it's a detail, but it's interesting to see that sometimes mathematics maps to simple constructs like anything else. So that's called the cross entropy. Then we have to measure our accuracy. So actually in statistics, this is quite complex to do that. It's not as intuitive as we may think, as everything in statistics. When we have a prediction, which is either correct or wrong, and the result, the ground truth, if we really want to assess the validity of an algorithm or system that makes prediction, we will have to take into account all the true positive, false positives, false negatives, and so on. We have to take into account the recall and the precision, which really compares all the cases. Because if we only take the accuracy into consideration, for instance, it could be okay to always output, yeah, this is the correct number for all 10 numbers, and we are always right on the prediction of a number. We are wrong for all others, but this is not reflected in our values. So this is complex, but in our case, we'll only take into account the accuracy. So the accuracy is the sum of the cases where we are right, so the true positives, the true negatives, divided by the number of examples we have. Okay? Just beware of statistics. So, let's see some code. So, we are going to use TensorFlow. TensorFlow is a library from Google, and as the name gives, the point in TensorFlow is to build a flow of mathematical operation on tensors. So that can be scalars, vectors, matrices, or n-dimensional tensors. We build that in a symbolic fashion. So we tell TensorFlow how our operations are built. Of course, there are simplifications for that. And knowing the symbolic construction of our operations, TensorFlow will be able to perform derivatives automatically, and then to implement the gradient descent algorithm by itself. So in Python, we just have to import the read dataset method from this package and call it with the mnist parameter. Tell that we want the results to be encoded as one hot. And the first time it will download data from anywhere, extract them locally, and you're fine. You can investigate a bit the content of the result. We have two sets of training. We have a set of training images. So we can see it's NumPy ND array, so n-dimensional array. NumPy is the library for mathematics computations, below or aside TensorFlow. We can check the shape, so we can see that we have 55,000 examples, and each of them is a vector of 784 pixels. Ditto for labels. It has almost the same shape, except that it only has a vector of 10 values for each example, and we can see that it's a one-hot encoded vector for 7, I guess. So, now that we have our structure, we have to define the TensorFlow, the flow of tensors, let's say, the graph of expressions. So we can't use directly Python expressions, otherwise TensorFlow will not understand anything. So we have to build an abstract syntax tree. But we'll see it's quite simple. It's mechanical from this diagram. So we start from the pixel on the left. These are inputs. So we just have to define that as placeholders for TensorFlow, meaning that we will give you the actual values later on during the training phase. We define them as floats, and we don't know the number of examples we have. We'll see later on. We just tell TensorFlow that you need to reserve 784 values for each input. Okay, then we have to define all these weights for our weighted sums. So this time it's called the variable in TensorFlow. It will have to compute the values. We specify that the size of these weights is 784 per digit, so by 10, so that's a matrix. And we initialize everything to zeros. Okay, then we have to compute the weighted sum. So I don't know if you recognize that, but a weighted sum of this kind is actually a matrix multiplication. I won't prove that graphically, at least, but that's all we have to write in TensorFlow to perform this very complex computation. I don't know if you remember, there are two loops. And the fact that we do that and not in Python or whatever, is the good side is that it will be vectorized, either on CPUs or on GPUs, hopefully. GPUs are made really to perform this kind of computations, and especially the GPUs used for neural networks that don't have a graphical output. Good. Then we have to perform our soft comparison, so the softmax and the comparison with the ground truth. The function we want to use is the cross entropy. And I don't know if I forgot something. And in TensorFlow, it's nice. We already have a function for that, which is called softmax cross entropy with logits. So logits, it's not a clear word. It's a shortcut for multinomial logistic regression. And once again, we have a problem with naming. I don't know if I already said that. Because linear regression, the first problem that we saw, was to find a numerical value in a continuous range. Here we are talking about logistic regression, which is called a regression, but the point is not to find a value, it's to find classes. So it's a classification problem. Anyway, the method is called this way, that's life. We just have to tell it that our logits are y hat. We can't use a hat on y in Python. And the labels, the ground truth that we have is y, that we will inject at training time. And then we have to compute the average, the mean of all variables. So we have to divide by the number of examples. And it's called a reduced mean. I don't know if this does something else, maybe, than just computing an average. Good. Then we need our gradient descent. We won't implement that. We just ask TensorFlow, okay, give me a gradient descent optimizer with the learning rate alpha that we'll see later on. And then we have to tell this optimizer that it has to optimize, to minimize actually, our cost function j, which is the softmax and so on. Okay? So, 3 lines of declaration, a bit of computation, and we are done. Mojito time or beer time. We'll see later on for the break. Okay, so now we have to link our examples and ground truth results with the placeholders that we have defined. So we build for that a Python dictionary, which just maps the 2 variables. And then let's make some space, compact a bit, and we have to perform our loops, our training loops. So yeah, for that purpose, so far we haven't performed any computations at all. We have just started to build a graph of tensor operations. And in TensorFlow, the actual computations happen in a session that's with the with statement in Python, which is a bit like try with the resources in Java. That's where or when TensorFlow will figure out how your hardware is configured, what do you have as CPUs and GPUs, and it will map with the second line. That's where it will map everything to the appropriate computation unit. So first we have to tell it to initialize whatever global variables it sees fit. And then we can iterate over our number of epochs. So I guess I haven't said that an epoch is when we process the whole set of data. Okay? So that's in our curve, that was the x-axis, as we'll see that again. So we just tell it, okay, perform runs of forward and backward propagations using step, which is your goal, is to minimize the cost function, using the dictionary, which maps images and results. Okay. That's 12, I think, lines of code, and we have everything to implement what I've just drawn on screen with the progress and so on. 12 lines. If we want to progress the monitoring, we still have to decorate a bit our code. And what we want to monitor here is the accuracy. So, naming our ability to recognize digits properly. So, what we have to compute is to compare the argmax. This function tells which digit has the highest result, both on our prediction and the ground truth result, and we compare if they are equal. If it's 1, yeah, we are right. If it's 0, we are wrong, or booleans. Then we have to convert that to floats, and we compute the average over all examples. In each step, we ask TensorFlow to compute the accuracy using, once again, the dictionary, and we print it or we plot it as I did on this slide. So, we have the number of epochs as x, so we'll only, but that's already really a lot, we'll perform 10,000 iterations over all our examples. And when we start our algorithm, we have random or actually 0 values. So our let's not call that a network already, but our system will output mostly random values. So it should be right 10% of the time. We'll start from there. So let's run the algorithm. So we see that right away, in a few epochs, or maybe even the first one, I don't think so, we jump to 2/3 of accuracy, 66% or around that. So that's quite good. And we end up at 86% of accuracy. All that with 12 lines of code and 10,000 epochs. Okay, apparently we haven't reached an asymptote. So we could go further, we could compute further examples, but this is consuming electricity. That's not green computing. So if you think that 86 is good, don't forget that if you want to read a complete zip code of 5 digits, usually, you have to be correct on all of them. So you have to multiply the accuracy, and that means 47 accuracy. So with this system, if you want to read a zip code, you will be wrong half of the time. Unusable. So let's try to go faster and increase the learning rate. Okay? We reach a better result faster, and we go faster, 90% of accuracy now. But we still don't have an asymptote. So let's increase again, multiply by 10 every time. We go, the slope is even steeper. We reach 92. I guess we have a kind of asymptote, but let's go a bit quicker with the learning rate set to 1. Okay, now we have a clear asymptote. We could have stopped our learning around 5,000 epochs, maybe. Good. So, what if we go further with the learning rate and double it? Okay, so our algorithm is not converging, it's oscillating. We still manage sometimes to reach the maximal accuracy for this system, but it's really not reliable. So we have to be careful with the learning rate. So let's go back to 1. Let's try to introduce bias, which is small constant additions to the system. Actually, it's on a separate slide because I was too lazy to update the former one once. But so in TensorFlow, we just have to define another set of variables, 10, 1 per digit. We have to include it in the multiplication. There we have the magic of Python, which supports, how is that called? It's not dispatch, the plus operator on the result of a multiplication, which is a tensor. It makes so that TensorFlow is able to understand that it's a dispatch this way. Anyway, so we add these biases. We try on our graph. It's very subtle. I don't even know when it starts. Okay, I guess you haven't seen anything. It doesn't change anything. I should compress my slides. So the best result we have found so far is not that good. I mean, it seems to be a good idea, but it's only reaching 93%. I guess that makes 70% of accuracy on the zip code, so it's not good enough. So researchers have researched, and they figured out that maybe they should take inspiration from the human brain how we are supposed to be the most clever species on Earth. And in a human brain, there are about 80 billion neurons, and each neuron is connected to about 10,000 other neurons via synapses, which are connection sites. They are at the end of axons and dendrites. And the total length of all the axons and dendrites in our brain is about half the distance from here to the moon. All that in our brain, our nerves, and down to our toes. And so the electrical signals that are received from synapses or dendrites rise up to the neuron cell body, where they are apparently added, summed up, and if this sum gets over a certain threshold, then the signal is sent not back but forward to axons, so other pieces of the neuron, to other neurons or to other muscles, and so on. So that's what we'll try to do. Shall we take a break now or later? Do you have any questions so far? I guess I'm also at the middle of the talk. I have to make a subtraction to remove 30 minutes. Shall we go on a bit, or do you want a break now? Everyone is asleep, or everyone wants more. So maybe we can do all that in a row. It's almost as you wish. No? Okay, so let's say no one is moving actually. Okay, so let's go on. Deep neural networks. So we had our simple system that we will call with a single layer of weighted sums. And let's make some room on the screen. We have to ask for bigger screens next year. So we're going to try to add a second layer, a third layer, a fourth layer, and up to 5 layers, because what researchers have figured out is that was a good idea. They had to make many iterations to figure that out. And they decided that we could have a first layer with 200 of these weighted sums, a second layer with 100, 60, 30, and in the last layer, 10 weighted sums for each digit. Okay? And then the softmax to convert that to probabilities between 0 and 1 and so on. Good. So what do we do for that in the TensorFlow? So we just define more variables. We have the same placeholders. Our inputs and our ground truth values haven't changed. We just define 5 layers of weights and biases. So biases is the small value that we add at the end of our matrix multiplication. So the question is, how shall we initialize these variables? So formally, we just initialized them with zeros because they were different. They were all linked to a different output. In this case, if we do that, we will always have the same weights everywhere at start, and there will be no differences between the nodes in the different layers. So we have to break this kind of symmetry. So for this purpose, we will initialize all the variables, the weights at least, with using the function truncated normal, which is another way to say initialize that to values that are close to 0, around 0, and which respect a regular normal distribution, a Gaussian distribution, with the bell curve. And we have to tell the dimensions of these tensors, which are matrices here. So we just have to, every time, to use the dimension of the former layer. So we start with 784 pixels. So our first matrix of weights will be 784 by 2000, because we decided that we wanted 2000 nodes. Then we initialize the 200 biases as well. And in the second layer, we have 200 weights multiplied by 100 and so on, up to the 10 last nodes for each digit. And we have sigma that tells the mean the mean between the values for the normal distribution. Let's not matter. Okay, so we have defined, now we have to define our layer functions. So that means our matrix multiplications, our weighted sums, plus the bias. And this doesn't change much for the last part. We just compute a softmax on the last layer. This, actually, the internal layers are called the hidden layers at first. Now we always have hidden layers, so we no longer call them that way. So, as I said during the human brain video, the neurologists thought at that time, and still think, that the output of a neuron is not directly linked to the sum of the output. Actually, this sum is given to an activation function that will act, that will filter out values that are too low. So the output of the neuron will trigger only if the weighted sum of its input will pass a certain threshold. And they thought at that time, maybe they still do, I don't know, that this function was a sigmoid. And the sigmoid is this kind of S-shaped function that shrinks the range of values, of input values, into a small range that we can decide depending on the actual sigmoid function. And in our case, for logistic regressions, we'll be using the logistic sigmoid. We don't even call that the logistic, we just say sigmoid. So for the record, its implementation is that we raise the input value, or minus the input value, we exponentiate it, and we compute the inverse of that plus 1. So the point of the exponentiation is to have a ceiling quite quick. And as we can see, this function is almost linear within the range -2 + 2. So if we keep our inputs normalized, not too far from 0, not too large, not too small below, too large below 0, it will keep that in this almost linear part. Otherwise, all other values, large values in absolute, will be shrinked to -1 or 1. And this function is symmetric around 0. I said -1, but it's 0 and 1. And the sigmoid of 0 is half. Okay? It's not really important, but we are going to inject this activation function in our network or graph of calls. And that's this small unit of computation is what we now call a neuron. So it's performing a sum of weighted products, adding a little bias, flushing all that through an activation function, and then outputting this the result for whoever wants it. Okay? That's a neuron. So let's try that. We were, so I haven't shown in the code the activation function, but anyway. So the last time with our one-layer network, we were at 93% of accuracy. So we have changed our neural network architecture. So we have to restart our research for a good learning rate. So let's restart with a small learning rate, because as we've seen, choosing a too large one may be quite dangerous. Okay, so with 10,000 epochs, we are not learning anything. We are just a bit above the random result of 10% accuracy, while we learned much faster with the simple one-layer network. Okay, let's increase the learning rate. Nothing. Okay. Let's increase it. Oh, around the 4000th epoch, now we are starting to learn. We have a bit hiccup near the end, okay? So that means that our learning rate is too large. But let's try to go faster, because 10,000 epochs is really too much. Okay, so we have quite a chaotic beginning, but we are now reaching an asymptote. The algorithm seems to be converging. There's no point in going further. And we reach a 100 accuracy when reading these digits. Isn't that good?
The spikes, is it local maximums that they're trying to get rid of?
No, I don't think so. It's just that our alpha rate, if you remember the curve that we have between mountains, let's say, I should make a drawing for that. It's just that our alpha rate is too large, and in some cases we outshoot the target, and we go very far from the bottom of the pit where we used to be. So we will see more adaptive learning rates later on. But okay, despite these hiccups, we manage to converge and get 100% accuracy. So that's very good. Can we still speed up things? Because 10,000 epochs is quite too much. I don't know if you realize, I don't know how many parameters we have in these neural networks. But every time on each example, we have to compute the forward propagation path. So that makes a lot of computation. We want to save electricity. So when we run on an epoch, I said we perform loops at each epoch of forward and backward propagation paths over our whole training set. But do we have to process the whole training set every time? Let's try to do batched epochs. So we split our training set in two, and we just train the network on half of the examples, then perform our backward propagation path that updates the weights, and then we do that for the second half of the training set. And then, of course, you can figure out that we'll try to split in 4, etc. So let's try that. So that's our previous result. We had alpha equal to 1, which seems fast, and a single batch. Now, okay, I don't remember what this is. Maybe the title is wrong, but anyway, let's move on. Oh, okay, yeah. I reduced the number of epochs from 10,000 to 500 because I want the result to fit in only 500 epochs. So if we do that, we have just the beginning of this curve, and we don't converge yet. It's not enough. So let's try it with 2 batches. Let's cut the training in half. Okay, so it's chaotic, but we seem to go somewhere. Let's try with splitting our training set in 5. Okay, still chaotic. Doesn't smell good, but we are learning faster. We only have 500 epochs there. Let's try with 10 batches. So that's another hyperparameter of your neural network. And that's something that you have to try with trial and errors. Okay, so 10 batches. We can do better, maybe. Let's try with 100. Good. Very good. So in 100 or a bit more than 100 epochs, we managed to converge, and we managed to reach 100% accuracy. Better? Good. Oh, I even did that further. So in far less than 100 epochs, by splitting our so our training set was, yeah, it's written there. Our training set was 55,000 examples. We split it in 550. So we just have 100 examples per batch, and the system manages to learn. So we could go further and just run that, the whole forward and backward propagation for each example. That's called stochastic gradient descent. And it sounds a bit random, because once we try to teach him to recognize a 7, then an 8, then a 5, which are very different numbers. So I guess the system could be completely lost. It's you try to drive it to one direction, then completely the other ones. I guess it must end up being mad like this cat. Okay. So if we do that, we have a more erratic progression. The learning rate should be reduced, because if you switch direction, you don't want to switch too far and once again overshoot your goal. So that means that you have a slower progression. So let's try that. No, I haven't done that, but I haven't done the slope. But some people say that you should always do stochastic gradient descent. Another problem is that if you think about the algorithm from a mathematical point of view, the first pass of forward propagation is something that you can dispatch over multiple CPUs or even multiple machines if you need that, and you just have to sum all the results at the end. On the other hand, the backward propagation phase is something that you are not supposed to be able to parallelize, because you are updating all the weights. So mathematically speaking, that's not something you can split over multiple GPUs or machines even. But in real life, some researchers have found that you can still do that in parallel and merge the results from time to time. I guess you have a longer training rate, but as you are doing that over multiple GPUs or machines, it's still winning in the end. But I guess I will skip this part. It's just to tell you that instead of the constant rate that we had so far, constant learning rate that we had so far with the gradient descent, we have several other algorithms that find or use a more adaptive learning rate. So for instance, the names maybe don't matter. It's momentum. We have just one step of memory, so we remember the momentum we had for the previous step. And Adam is the most complex one. We have still adaptive momentum, that's the name, but we have different momentum per parameter, and we use a sliding window to, or probably an exponential average, it's called, to remember the learning rate without having to keep all the memory, in memory, all the learning rates since the beginning of the training. So you can maybe see on these different schemas that some algorithms clearly overshoot the target. For instance, the green one, it really goes far away at the beginning, and then it reaches the goal, which is the star, and it seems to reach it faster. It depends. So there are many more other variations. So my point was to say that this is another hyperparameter for your network. You have to choose the learning rate, what kind of actually adaptive learning rate you want. You have to choose the number of examples in your batches and so on. So that this is really a multi-dimensional problem that you have to optimize if you want your training to be as fast as possible. Doing all that is not supposed to change the outcome of your result, the accuracy of your system, but it changes the training time. So your money and the time it takes to make an iteration, a complete one. Okay, so yeah, so I show several curves. So Adam goes faster. So we only have 100 epochs on this diagram, and we converge very faster. At first, we needed almost 50,000 or 10,000, I don't remember. Okay, so then another progress that we made is that we have a problem with large, deep networks, is that if the values go too large, we don't have any gradient. I don't know if you see beyond 6 or 8 or whatever, the slope of the sigmoid is flat. So we don't have any gradient there. So that means that we have nothing to update our parameters at each step. So it's maybe not a good idea to use the sigmoid, actually. There are many mathematical functions to choose from. What we want is a function that is continuous, derivable, that rise up, so I guess it's continuous, or increasing, monotonous, we say. So there are many to choose. 10 is a good one in some cases, but actually the researchers went for a very simple method, function, which is called the rectified linear unit. So it's a linear function, but just cut for all negative values to 0. So that means that we won't have any gradient there, but it's just a matter of then changing our normalizations. And the good point is that the derivative of this function is even simpler. Okay, so let's try that. So this was the former examples that I hadn't shown in detail with the 100 examples per batch, the Adam gradient descent algorithm, and we used the sigmoid, so that was the former result. Let's see what we have with the Redu. It's even faster. So that's something else that you have to choose in this time, the architecture of your network, which activation function you want to choose. So, are we done yet? We have a simple deep neural network, only 5 layers. We have 100% accuracy on the training set, and I have presented many ways to speed up your training. So, is everything fine? No? What's wrong?
I don't know.
Ah. 100, so champagne? No. We have 100% accuracy on the training set. What does this prove? Nothing. Our system is meant to make predictions in the future on, in this case, images, digit images that we have never seen. Okay? So we have no information for this topic of the accuracy of our system. So this is wrong. We need to split actually our training set in 2, or actually 3 parts. First, we'll keep some examples aside called the test set on which we are going to measure our accuracy. Okay? And actually, we'll keep another set of examples on which we will tune our neural network. We will use this set for tuning whatever, the architecture or whatever. We should never make decisions on the architecture of our deep neural network depending on the result of the test set. Otherwise, you are about to contaminate the accuracy on the test set. Is that clear? Okay, so let's measure the accuracy on the test set. Oh, fuck. So we only have 98% of accuracy on our test set, while we reached 100% accuracy on the whole set of examples we had. So what happened? That's called overfitting. Actually, our system was so good that it learned by heart all the images that we gave. So it was very good on these images, but then it's not able to generalize and to give relevant results on images it has never seen. Okay? It's like if you remember a question, the answer for this question, if we change a bit the question, then you are no longer able to answer. It's the same question. Okay, and 98 accuracy is not acceptable. If we raise it to the power of 5, it's not acceptable. So there was this nice picture for overfitting. You are asked to build a bed. You figure out how this guy or girl sleeps, always in the same position. Okay, that's a bed for you, a mattress at least. Okay, you don't generalize. Okay, how do we, too early. So what do we have to check regarding this overfitting? So on top we have our accuracy curves. What we should monitor as well is our learning curve. Here is in blue the learning curve, actually the cost function, the loss function on our training set. Good. The goal of the algorithm of gradient descent is to minimize this one, so it reaches 0. Good, we are good at that. But then what happens on the test set? Okay, so we see that at first we very quickly reduce it, so we are able to have a quite good precision on the numbers, but then it starts to increase. And the difference between the two curves is the overfitting. And if it's raising, we have to stop there. So what we can do is stop the computation when it starts to diverge. Okay, but then we have to stick with 98% of accuracy. It's not enough. So early stopping is an option, not a good one. You may need more examples. In this case, we have 55,000 examples. It's fine enough. We can see from the curves, our problem is not that we miss examples. Okay, so we can add regularization. It's a way to limit it's ways, because there are several techniques, to limit, to prevent our neurons from learning too much, which seems a bit paradoxical. One of the techniques of regularization is a funny one. It's called dropout, where you actually just kill the neurons, Tarantino style. And at each step of the computation, Steph, you missed the best part. So at each step of the computation, you will select randomly maybe 25%, it could be as much as that, neurons, and you prevent them from learning. You exclude them from the computations. You have to rebalance the weights, but it's a technique that sounds a bit paradoxical. We want to learn something and we prevent our neurons from learning. But actually it gives very good results. Another way is to normalize batches of outputs. Normalization, again, is very important in neural networks. You don't want some of the neurons to output very large values when some others output smaller ones. So the goal is to have everything usually around 0 within a certain range. So batch normalization does that. And of course, we can think about architectural changes. In this case, I think that with the dropout, for instance, we reach something very close to 100% accuracy, which means human level intelligence on this. But this is still a very simple problem. We want to go further, and our goal, our ultimate goal, is to distinguish cats from dogs, you know that, or hot dogs, and perform that in real time so that we don't hit them while driving in an autonomous car. So the kind of neural network that we have seen so far, this one is called fully connected networks. Besides the dropout, all networks in one layer are connected to all other networks from the previous layer up to the inputs. And so in order to really recognize things, so no, I was wrong. The best result with this kind of network, even with dropout, is 98, apparently, from my notes. So I thought we reached 100. So let's pretend that it's not good and that we still have to find something better. Shall we have a break, or I can go on, I think. So, okay. Shall we have a vote? Do you want to break or not? Break. Okay. 15 minutes or half an hour? Okay, 15 minutes. What time is it? It's 20 past 15. So at 35. See you. Okay, so we're back. So as a reminder, we were working on a fully connected network. And researchers, so Yannis and others, I guess that was their solution. This architecture was their solution. We reached an accuracy of 98%. I thought it was bigger, but larger, but anyway. So once again, if you want to read a zip code correctly, you have to be correct on all digits. And in terms of probabilities, that means that you multiply the probabilities. So if each probability is less than 1, you will have far less than 1 in the end. So 98% accuracy is not something enough to fire everyone in post offices and replace them by cameras and computers. So that means that this architecture is not enough. So we need to go beyond fully connected neural networks. We have to find another architecture. And actually, we made quite a major error at the very beginning of the processing of our images, where we destroyed information. Have you noticed that? Actually, in the images, there's a very important information, which is that pixels are related one to another. They are close to one another or not. And we have destroyed this information by flattening our image in a vector. Okay? So the neural network should be able to figure that out back from the linear vector. But apparently, it isn't. So we have to find a way to exploit this locality information. And once again, if we keep considering humans as a relevant reference in terms of visions, even though some animals may be better than us, we should maybe consider how we process, or how we think we process, visual stimuli. So, I would like to play a game. No, but don't worry, the doors are still open. So I'm just, sorry? Okay. So I'm just going to show you some pictures quite quickly. So just try to think right away what these pictures make you think about. Your very first impression, okay? So what is that? So no, it's not a face, it's a can. This one, it's not a bird or a phoenix or whatever, it's an orchid. So no one is spying at the window, that's just frozen water. That's not a sleeping giant, that's just a snowy mountain. So I had to remove some other pictures to fit with the cock. But anyway, so I guess you got it. So this phenomenon, so yeah, I haven't aligned the picture. What a mess. So this ability that we have to recognize common patterns is called pareidolia. And we think that it has been selected by natural selection, because when you're in a forest, for instance, it may be life-saving to figure out that there are tigers' eyes between the leaves or whatever. This may increase your lifespan. So nowadays, we use pareidolia mostly for recognizing moods in smileys, but that's another story. So the point I think we should keep from that is that when we see things, the overall shapes are maybe more important, like colors or information like that. So maybe that's what's missing in our neural networks. What they can't achieve by themselves, they are not able to really correctly detect shapes. So we are going to see convolutional networks because there are several ways to detect shapes, and the one we are going to use is convolutional filters. So after the fully connected networks, we are going to see convolutional networks. And these networks will be actually much more suitable to recognize images like digits or much more complex images like cat, dogs, and hot dogs than this one. So convolutional filters, they seem a bit complex at first, but actually they are more simple. So we start from our initial image that I've shown here, and we want a resulting image that is processed in a way that it will be easier to detect shapes. So for instance, if we focus on this pixel in green, which corresponds to the purple one in the source image, we are going to consider the surrounding pixels as well. Here, with a 3x3 matrix, we could use a larger one. And we are going to apply what is called a convolutional filter. So there's no matrix multiplication there. We are just going to multiply pixels one by one using the orange weights, and we perform a sum on that. Okay? And we have to do that for each and every pixel in the image. So we scan the image. We can do that in parallel, of course, and so on. You can see that for pixels that are around on the border of the image, we are missing some information. Let's not bother about that. We can either pad the image or accept to lose, to reduce the dimension of the image. So, for instance, if we start from this cat, I'm using black and white pictures for the time being because it's simpler. If you consider RGB pictures, so with 3 layers of information, you just perform the same operation. It's just that your filter has 3 layers as well. But let's keep it simple. So if we use this kernel, the filter is called a kernel in this case, with only 1 in the middle and 0 all around, that means that we are using the identity filter. If we use this one with the 1s everywhere, and we divide by 9 just to keep the luminosity information, we are blurring the picture. I don't know if it's really visible. I should probably use a larger matrix. And there are interesting filters, like this one, which is sharpening the cat. I guess you can see on the fur looks like he just got out of the bath. And that's actually how, as far as I can say, or as far as I know, that's how filters work in GIMP or maybe Photoshop and so on. Probably with more advanced techniques. You can choose many settings and so on. But I think in GIMP, there's exactly an interface for inputting the matrix or the kernel for filters. So that's how it's supposed to work. So there are special cases of filters. Don't bother about the actual values, which are called Sobel filters, and which are used or can be used to emphasize edges. So here I've performed a kind of rotation, but if you can see on the picture, it's as if you were lighting the cat from top, I think, from left, top, right, bottom, etc. Can you see that on the picture? So this kind of filter is very interesting to detect edges. So we would like to use that in our image processing first, before using a fully connected network. The problem is, how do we choose kernels? For instance, for Sobel filters, different angles, and there are all the variations actually. We already have 4 choices. So which one should we pick? We don't really know for different images which Sobel filter of any variation will be useful. So the idea is to use multiple filters. So that will be one decision to make in your convolutional network architecture. And of course, we let the system figure out what the parameters of the kernels or filters will be. We will initialize them with random values around 0 as formally, and then we let our gradient descent or variations algorithm to figure out the proper values by themselves. Okay, so these kernels may, depending on the choice made during training, they may emphasize edges or other strokes or whatever. But then we still have images that have the same size of the input. And the point of neural networks are to synthesize information progressively until the end of the neural network, up to the final neurons that perform the actual classification. So we have to synthesize the information. Okay, so how do we do that? We need to pull information in one way or another. One of the ways is just to consider, so let's keep in mind that a kernel, a convolutional filter, will react to some edges, okay? We have several ones. On this slide, we only consider one. So if we have only zeros in a part of the image, that means that we haven't reacted to this stroke or edge or whatever. And a simple way of pulling the information and synthesizing the information is just to keep small windows on the images and compute the max of the value. If there was nothing, it will be 0. If somewhere we reacted to a certain stroke, we will keep that information. Okay, so for instance, in this case, we have a max pool with a 2x2 window. So we process 4 pixels at a time, and with a stride, so the step by which we move our window at each step of 2. Once again, there are many decisions to make. You can have larger windows, larger strides. You can even forget about some pixels, and or smaller strides that overlaps each other. Good. So this will be a basic block of a convolutional network. We start from the image. It's flat. It may have 3 layers. Let's forget about that. We apply several layers of convolution, sorry. Each one will react to strides or edges or whatever. And then we pull each layers in order to reduce the information. Okay? And we get smaller images at each step. And then we are going to repeat this block. So, for instance, this is LeNet 5 network. It's the architecture. So once again, this one was done by Jan Leuken, so the guy who was working on the MNIST database. And this one reached 100 or almost accuracy. So we start with, this time it's images of 32 by 32, maybe because they, I think they added borders, artificial borders. Then we apply 6 filters of convolutions. Here, apparently, they accepted to lose 2 pixels around the image, because we are already reducing the size of the image. Then we perform a max pooling. So we still have 6 images, but we divide by 2 the width and height. Then we perform another pass of convolution, this time with the 16 kernels of 10 by 10. Then once again, we perform max pooling. And then we complete with 2 layers of fully connected network with 120 neurons in the first, 84 in the second, and actually a third that will perform the actual classification with 10 neurons for each digit. Okay, so of course it took them time to figure out this proper or optimal architecture. But then they were able to achieve its 99.7 or whatever precision. And that's considered close enough to human level intelligence to be able to fire people in the post office. So once again, a great achievement of science. So overall, this network architecture has 60,000 weights or parameters. So at that time, in 98, it was quite a large network. So I guess it took time to train and so on. It was way before the GPUs. It was 99.2 accuracy, this one. And with variations, I don't know exactly, we got up to 95.75 accuracy. So that's enough. But well, it's not enough to detect cats and dogs. So we had to go deeper and deeper. So for instance, the GoogleNet architecture, which is play on word with the net architecture, had 22 layers, and I don't know how many parameters. And I guess this one won the competition on the ImageNet database. And then, since then, they have moved to other databases like Coco. And ResNet, I think, from Microsoft, is a network with 152 layers. And this kind of network needs, I think, weeks of training over several machines. And the pictures are much more complex. They have, I don't even know if it's still bounding boxes, maybe it's even segmentation. So we have the shapes of things. So it's really amazing. So if we go back to 2014, that was the architecture of the GoogleNet network. Its nickname is Inception because there are pieces of networks within networks. So it should remind you something. So this one on the ImageNet classification challenge had an error rate of less than 7%. So I don't know if it's considered on this data set as a human level intelligence, but I think it's quite close. So for these kind of challenges, we can almost consider that the case is solved. So how do we do that with the TensorFlow? Well, it's as usual, we have functions for that, so we don't have to write manually all the equations for computing convolutions and so on. We just have in one line conv2d, and that's it. So ReLU is the rectified linear unit, and then max pooling, and then we repeat the operation, and we end with the layers of fully connected networks as we've seen earlier. So TensorFlow is a very still generic library. So there are many operations, lower level operations that are not specifically related to neural networks. That's why neural network functions are in an NN package. And if you have really large architectures like the one we've seen for ImageNet, and of course for ResNet, you just can't represent that on screen. So you just have a list of all the layers, what they do, and you may even have noticed that there are that some information are skipping layers over there. So on a larger network, you can't represent that. You just have lists. So we can do even better in terms of abstraction and simplification for our implementation with the Keras library. So yeah, technically speaking, when you perform neural network computations on a machine, so you have your hardware with the GPUs and CPUs, You have a first layer of low-level hardware abstraction. For the GPU, it's libraries from NVIDIA, which is the leader so far. So you have CUDNN, which are specialized functions, and CUDA for the programming of tensors, but they are not called this way. For CPUs in Python, you have BLAS and Eigen, which are C libraries as well. All of them are C libraries with bindings for Python. And actually, Keras is a higher level library for deep learning and I think machine learning in general that can work with several engines like TensorFlow, Theano from maybe it was the one from Facebook, but I'm not sure they are on PyTorch now, and CNTK from Microsoft. And actually, Keras is now being integrated within TensorFlow as a Keras package, actually. So it has become the preferred way to use TensorFlow. And anyway, TensorFlow is really the leader in the pack. So we can write the LeNet 5 network with Keras. It's much more simple, actually. With Keras, you just define your levels, your layers, actually. You don't define operations, mathematical operations like matrix multiplications, adding the bias, and so on. No. You just describe the layers. So we start with this constructor, which states that we want to start with a sequential model. And then we have the first layer of 2D convolution with 6 filters, 5x5 kernel. I forgot to mention that we had, of course, an activation function at each step. So we use redo. And we say that the input values from our digit database are 3232 because we have added borders. Then we perform a max pooling layer with a pool size of 2, so 2 by 2 matrix, and the strides of 2, and then another layer of conv2d and so on. And then we complete with dense. So we flattened before, we flattened in the last layer of convolution or max pooling, actually, we flatten the values because we have as many layers as we have filters. We flatten that, and then we perform the 3 layers of fully connected networks, which are called dense in Keras, with the activation, and we end with the redo activation for the 2 first, and we end with a softmax. So it's really one line, of course, for more complex architecture, it will be a bit more, but it's merely one line of code per layer. And then we ask to compile an optimizer with this method function for the loss function, etc. And we want the accuracy metrics as output to process or to plot it. Then we ask the model to fit the training data that we have for that many steps, that many epochs, and so on. So it's much more simple. Okay, so 31 minutes left. Actually, so with this, now you've seen with the convolutional networks, with the variations that we have also seen in GoogleNet and so on, all the jumps between layers and so on. There are tons of tricks. It's really as if you are cooking something. So it's a lot of trial and errors. As you've seen, there are many possibilities in the different architectures, many possibilities for the hyperparameters that you can choose. I haven't talked about systems that allows you to find these hyperparameters by trial and error automatically. So there are systems, so don't think that you have to retune all the knobs by yourself. But of course, it's beyond the scope of this talk. So there are many things that we haven't talked about. So for instance, now the problem at hand is no longer to compute or to detect bounding boxes of objects. It's more to perform image segmentation, so that we are able on an image, for instance, in real time to detect that someone is on a bicycle and to separate the pixels that belong to the bicycle itself from the ones that belong to the biker. The next goal, but this is already quite advanced, is to perform that real time on video feed. So that means 25, 30 times per second. To perform that on visual video feed, like from regular cameras that we have in our cell phones and so on, but also from LiDARs. So this kind of radar, laser radar that spins on top of automated cars. I should talk about transfer learning. That's important because I got asked something about that during the break. If you want to, let's keep on visual examples. So if you want to recognize objects in pictures, but you don't have the same objects that the COCO database, for instance, which has hot air balloons and animals and so on, but you want maybe leaves because you're a botanist, do you really need to start from scratch and train a whole network with maybe 152 layers on your leaves images? No. Actually, you can apply transfer learning. The idea, but I think I have slides for that. Or at least we'll get back to. How can we choose the? Okay. Anyway, let's keep with the hands. The idea is to get a network that is already trained, because usually the winners or all the participants in a competition publish their result in GitHub. So you can retrieve from GitHub the architecture of a network that won some competition, including the weights. So it's an already trained network, but it has been trained on a certain set of images, and maybe there are no leaves in there. So you want to retrain this network, but keeping the things that it has already figured out. So actually, and it's very easy to do that in Keras, for instance, you will load everything, and you will tell Keras to freeze usually the convolutional layers of your network, and just to keep the last parts, which are the fully connected networks, free, and you reapply the training phases, but you don't touch the parameters from the convolutional layers. And actually, you are able this way to recycle all the detections that the early layers were able to perform, certain strokes, certain shapes, and then certain, I haven't elaborated on that, but we expect that the very first layers, the very first convolutional layers detect very small strokes, edges and so on, and that subsequent layers will detect assembly of these shapes, thus recognizing a round shape for a zero, for instance, or an oval one, etc. So the idea of transfer learning is to recycle that. So you retrain your the network, but you only change the parameters from the last layers in the fully connected layers, which really perform classification, actually. The first one detect shapes, and the last one perform classification on these shapes. So this can save you a lot of time. There's a new kid in town that is supposed to replace convolutional networks. It's capsule networks, so it's still under research. It's quite complex, but the problem with convolutional networks is that they are able to detect patterns that are present anywhere in the picture, but they don't really support rotations and other kind of modification, especially with the complex patterns. So there's an example with a dog that has a limp in the face, and so his mouth is a bit bizarrely shaped, and convolutional networks usually don't detect that, or you need to train them separately for that. Okay, so capsule networks are still in research. Recurrent neural networks, so I haven't talked about that, it's quite complex. They are aimed at processing series of data. So when you use convolutional networks that are very good at processing images and shapes, they only work one image at a time. You can actually apply something I don't really understand, but you can apply convolutional networks on other data like sound waves, and probably text and so on. But the problem is that they only focus on one sample at a time. If you have samples that have a temporal relation, you lose everything in the process. So recurrent neural networks, they started first by duplicating networks. That's simple. You just pass information from the previous frame in a video or the previous, I don't know what, character in the text, and you feed that to the next layer. So of course, this causes lots of troubles because you get very large networks, and there's been tons of research for that with the LSTM and many variations about this idea. And nowadays, we are really able to process sequences in a very good fashion. Let's skip that because hopefully, I hope that this talk was interesting enough so that you may want to go on further and learn more things about neural networks. So I have a set of videos. So if you want to get the link, it's time to get your cell phones. If you have 3 hours or 2 hours and a half, I recommend you this video from here 2 years ago. Martin makes much less introduction, less details on algorithms and so on, but I hope that you grabbed everything today. But in exchange, he goes much further in the description. So he talks about NLP processing and so on, and gives also more details that I had to skip. So I recommend this video if you have 2 hours and a half. There are tons of resources on the internet. I don't know this one. I don't know why I put the slides here. But I guess, yeah, the talk from Martin, he works at Google, is part of this crash course from Google on machine learning. So I think there should be very good content in there. Then, if you want to invest in MOOC, so Andrew Ng, I don't know why I have animations on there. Andrew Ng is really a great guy. He's a great pedagogue. Do we say that in English? He's very good at teaching. So you have to speed up a bit the videos, but he talks quite slowly, but he's very good. So he founded the Google Brain project not even 10 years ago. He founded Deep Learning AI, so that's where you will find his courses on Coursera. He's also the co-founder of Coursera. And really, his MOOCs have been followed by millions of people, at least the old one, the obsolete one. And now he's working, among other things, on Drive AI, which is one of the companies that currently have automated cars in somewhere in Texas, or I don't know. But they are working right now. So be careful. This is the obsolete, I would say, machine learning course. It's very interesting if you want to do math by hand. So it's using MATLAB and Octave. So if you want to implement gradient descent by yourself and other funny things, vectorized multiplications and so on, it's a very good course. It's supposed to take you 11 weeks with, I don't know, 5 hours per week. I don't know the rate. But nowadays, it's a bit obsolete in terms of framework and level of abstraction. So This one was from last year, so it's much higher level. It's split in five topics. So you mostly have to take that in order. There's a very practical part in the third section for structuring machine learning projects. That's where he gives many of the recipes to how to monitor things, how to figure out whether you lack some examples or you already have too much and the problem is in the architecture and so on. And really the guy is really great. So, don't have any image, but on FastAI, they also have a library for on top of, I don't remember what, and they are told to have very good resources on the internet. So it's supposed to be a very good MOOC. If you want to go in the autonomous car industry, there's a nano degree on Udacity. It's for 9 months. And I don't know how many hours per week. So the first one, the first trimester, I guess, is quite generic. And then they go to really things specific to autonomous cars. So I think it's really if you want to go there. This one, so that's the one I told you. He writes very good articles, really on computer vision. So it's really on images and so on. And no, that's the book. I'm confusing, sorry. So this book is supposed to be quite mathematical. So it's a reference, but I don't know about it, but you can get for free on the net. This book, no, I wouldn't recommend it. This, no, it's too short. It's a good book, but it's a bit frustrating. So I don't know if that's Manning. I don't think that Manning is here. But this book is from François Chollet, the author of Keras, who works at Google. That's why Keras is being inlined in TensorFlow. And this book is really a very good reading. So it's focused on deep learning. The other one is really, the previous one was on machine learning in general, and it's too short. This one is really, really interesting. I really recommend you. So I still love books. MOOCs are great. Yeah, that's the MOOCs, the MOOC. So MOOC is massive open online course. So I don't know if you know that, but in Coursera, I should have introduced that because some people didn't know. On Coursera or Udacity or other platforms, you can have access to online courses. That means videos and slides. And usually if you pay, so some courses are free for just reading, let's say. And if you pay some more, you can have access to exercises, which are usually performed in Python notebooks, Jupyter notebooks. And you can have a certificate in the end if you pass the exam. So you can put that on LinkedIn. So massive open online courses are the way to learn now that you have left university and so on. So really, I recommend you to follow MOOCs, being the one from Andrew Ng, FastAI, or this one, which is really focused on computer vision. But this guy is great. He also writes very good articles on his blog. So you have the URL here. So we have 15 minutes. So either we can go back to bed or maybe try some questions. But you have to yell, because I don't see anything. Yeah?
Can it be accessible in a GitHub or something? I mean, to play with the code that you showed here.
Which one?
I mean, all your code in Keras and...
all the code, you can find it anywhere on the internet.
No, I mean, not Keras and TensorFlow, yes, it can be, but your slides.
Yeah, the slides, I will try to publish them. The problem, as I said, is that I have tons of animations. If I export them and videos and so on, so I can't really publish the PowerPoint. If I publish them as PDF, it will miss most of the content. So I have to flatten the animation first to be sure that I don't miss anything. So I'm doing this talk in Devoxx Keras next week. I will try to publish the slides definitely, I guess on my GitHub account or anywhere. I don't know if we have notifications on Twitter, but I guess I will post that on my Twitter. So you have my name somewhere there. And anyway, if you want to play with this example, NIST or any other neural networks that I've talked about, you can find them on the internet. What my code was missing is the processing of images also. So sometimes the images have not been processed, you have to flatten them, or you have to normalize the inputs and so on. So there's a bit of curation, as I already said, that takes a lot of time. And then there's the code to graph things, but actually the graphs are very easy to do in Python with matplotlib. It's a few lines of code. Python is really very good for that. I wouldn't write a large program with it, but...
In the book, Machine Learning with Python, how much Python do you need?
No, you don't need Python. If you don't want to practice things, you can read Python if you know Java or whatever. There are a few concepts like tuples. Of course, some syntax are different for function definition and so on. But if you know Java or I guess JavaScript, you should be able to read Python in a sec. So don't worry for that. So there was a nice question about local minima that I wanted to draw a picture for that as well. So some people were asking whether our gradient descent algorithm could be stuck in a local minima. That's an issue we have with the rules systems. I don't remember the name. And in their algorithm that I think, if I recall correctly, is called the simulated annealing, they choose a set of parameters first, and they evaluate, of course, a kind of loss function. And they jump with random values to similar places, and they try to figure out whether they get a better approximation of the result or not. And this algorithm is meant to jump outside of local minima. We don't have that in gradient descent, except that I think there are variations that also add some kind of random jumps sometimes. But some people think it's not necessary, because if you think of the first image I displayed with the ball that was rolling down the mountain and so on, we clearly have a local minima. If you think about a lake in a mountain, the bottom of the lake is a local minima. But if you want to go down the river, down to the ocean and so on, you probably have to jump a bit. But this was a two-dimensional problem. If you think about the real problems which are really multidimensional with many, many, many more parameters, the saying goes as that there's always an axis on which you can make progress and get out of the local minima. So in practice, apparently it's not a problem. And if you want to learn more, I think there's a session on Optaplanar, which was used to make the planning of Devoxx. And I'm sorry, I didn't check the planning early enough, because there was a hands-on on TensorFlow, I guess, and it would have been better to have my talk first. Who was in the TensorFlow hands-on? Okay, not many people. Okay, so either but the room was full, but either they didn't came. But it would have been nice to have some practice afterwards. So yeah, if you want to go on deep learning, you need a lot of time. So I broke my back, so I had 5 months of time for that. So I wish you the same. No, it was nice for that. Okay, we still have 10 minutes left, or we can get a beer or mojito. Okay? Thanks a lot, and if you have questions, I'm on Twitter. Stefan said that you are supposed to rate. I'm especially interested in constructive comments. So thanks in advance.